series on complex analysis for undergraduate students. Today's lecture is on evaluation of real improper integrals part 2. We are learning to evaluate the improper integrals using the residue theory. Today we will learn another method for another kind of improper integrals. So, today we will learn about the improper integrals which are involving sine and cosine functions. The residue theory can also be applied to the evaluation of the integrals of the form minus infinity to plus infinity integral of fx cos tx dx, or the integral of the form integral from minus infinity to plus infinity fx sin tx dx. These integrals are very useful when we are evaluating the Fourier integrals, or we are actually calculating the Fourier series. So, evaluating the or finding out the coefficients of the Fourier sine and cosine series, this kind of integrals appear. Here we would be first assuming that fx is satisfying all those conditions which we have learned in the last lecture, that fx is again a rational function which is can be ratio of two polynomials px and qx, and this p and q are both satisfying the condition that the factors to them are not common to each other, and the degree of the q, that is the denominator, is at least 2 degrees higher than the degrees of the numerator. So, we are having and moreover this qx will not have any real 0. So, on fx we have used, that is all the conditions which in the previous method are being imposed, all those conditions are also valid over here, are being imposed over here. Moreover, now we do have integral of the form fx into cos tx or fx into sin tx kind of function. Actually, these integrals or these functions we can use if we do use only one corresponding complex integral of the form fz e to the power I t z. And what we would do is we would like to change this integral to a contour integral of the function fz e to the power I t z over some contour c, and this contour we would choose as closed contour. Here when I am choosing this one complex function where fz into e to the power I t z, we do know by Euler's formula that e to the power I t z we could write it as cos t z plus I sin t z. So, if I am writing over here, this contour integral could be written as in the form of two contour integrals. One would be fz e to the one fz times cos t z and plus I times contour integral of fz sin t z. Thus, what we would get, we get that the whatever answer to this contour integral we are getting, we just here it is also a complex value, and whatever the answer we are getting is that would be a complex value. So, we just get it, compare the real and imaginary part, and accordingly we would be able to get the integrals along fz cos t z and fz sin t z. And again, as in the previous theory we had moved, that what we have done is we had used this Cauchy principal value and tried to show that this would be actually ranging to the integral minus infinity to plus infinity fx e to the power I t x dx. So, let us see is how we are going to do. First, we will take this t to be positive and real. So, this contour integral fz e to the power I t z dz, this again in the as in the previous method we would use this contour c as the semicircle bounded by the real line. So, f is has a and what we are assuming is that since fz is of the form pz upon qz, where p and q both are polynomials and q is not having any real zeros. So, what we are having is qz would have zeros which are complex numbers. Again, what we would consider as in the previous method, that the zeros of qz, because it is a polynomial, so it will have isolated zeros only. So, the zeros of the polynomial qz would be actually the poles of this function fz e to the power I t z, and thus we would go ahead with the residue of the poles which we are having in the upper half plane of the function f z e to the power I t z, and using that we would use this Cauchy principal value. So, we are having the poles in upper half plane. So, by residue theorem we could say is that if I do take this integral in the closed and we would choose this circle such that this semicircle such that all those number of poles are inside this circle. So, inside the interior to this closed contour C, what it says is that by residue theorem we could say that integral along this closed contour C would be nothing but the 2 pi I times summation of residues of f z e to the power I t z, where summation would be all at all the poles which are interior to this contour C, and this contour C is actually consisting of two paths. One is the semicircle, another is the real line, or that the real axis. So, we are using this semicircle of the radius r. R is chosen such a large such that all the poles of the function f z e to the power I t z are interior to this semicircle, and we are choosing the this other boundary as real line from minus r to plus r. So, as in the previous method we are writing this by residue theorem, this would happen. Now, as in the previous method we had gone, that is, if I treat this integral minus r to plus r f z e to the power I t z d z, we see this is on the real line. So, this contour we could say is we could write it as minus r to plus r f x e to the power I t x d x. Now, this integral we have to evaluate. This integral is equal to this integral minus, that is the integral on the closed contour C of f z e to the power I t z minus the integral on the path S, which is the part of which is a semicircle of f z e to the power I t z d z. Now, what as in the previous method, here also will show that when f z is of the form p z upon q z and the degree of q z is at least 2 degrees higher than the degree of p z, this integral along the semicircle would approach to 0 as r is approaching to infinity, and thus we would get that the value of this improper integral from minus infinity to plus infinity f x e to the power I t x dx could be given as 2 pi I summation over the residues of f z e to the power I t z, where the summation would be varying on the all poles in the upper half plane. So, what now we require is that as r is approaching to infinity, integral of f z e to the power I t z d z on the contour S must approach to 0. So, let us first see this portion here. Let us take now my integrand is f z e to the power I t z. Let us first see what is e to the power I t z. E to the power I t z, z is a complex number, we could write it out x plus I y. So, just substituting z as x plus I y, we would get e to the power I t times x plus I y, which would give, the first thing is that e to the power I t x plus e to the power I t into I y, that is e to the power minus t y. So, we would get this is equal to the absolute value of e to the power I t x into absolute value of e to the power t y. Since we do know that for the complex numbers x and y, absolute value of x into y is equal to the absolute value of x into absolute value of y. Now, absolute value of e to the power I t x, we do know e to the power I t x by Euler's formula, that it is cos t x plus I sin t x, and its absolute value is always 1, because cos square t x plus sin square t x would be 1 for all t and for all x. So, this would be e to the power mod the absolute value of e to the power minus t y. E to the power minus t y is a real number, so it should be same as the e to the power minus t y. Moreover, whatever be this y is we are taking this on the semicircle which is in the upper half plane, that is y is always positive, and t we have taken a positive real number. So, both t into y, this is positive. So, e to the power minus t y would be a number which is more than 1, because e to the power x for x positive is always greater than 1. That says e to the power minus t y, this should always be less than or equal to 1 for all y positive and for all t positive. So, what we have got actually from here, that the absolute value of I t z is always bounded above by 1. What it says is, now if I take the integrand, so now we have to show that this integral of on the contour S of f z e to the power I t z is approaching to 0 as r is approaching to infinity. On this S, this semicircle, if we are going with the parametric one, or you could say is a polar one, then z is r e to the power I t on this one. And what is my the formula, this parametric equation of this semicircle S, that is z is equal to r e to the power I t for t ranging from 0 to pi, 0 to pi. Now, f z e to the power I t z, this absolute value would be actually absolute value of f z, or you could say modulus of f z into modulus of e to the power I t z. Modulus of e to the power I t z is less than 1, just now we had proved. That says is this should always be smaller than or equal to absolute value of f z. Now, f z we had already assumed that it is of the form p z upon q z, where p and q both are polynomials. The degree of q is at least 2 degrees higher than the degree of p. So, again as in the previous method, for z greater than r, this p and q we would start, let us say p is a polynomial of say degree n, then p z we could write as a n z to the power n plus a n minus 1 z to the power n minus 1 and so on, plus a 1 z plus a naught. Now, using the take this z to the power n common from here, because we are taking this z is greater than r, we could write it as a n plus a n minus 1 upon z and so on, plus a 1 upon z to the power n minus 1 plus a naught upon z to the power n into z to the power n. Now, take the absolute value of this one. So, absolute value of or modulus of p z would be, now we are going to use the result, that is mod of x plus y is less than or equal to mod of x plus mod of y. So, we are getting is less than or equal to mod of a n plus mod of a n minus 1 upon z, and that we are using is mod of x into y is mod of x into mod of y. So, this is mod of a n minus 1 upon mod z plus so on, mod of a 1 upon mod of z to the power n minus 1 plus a naught upon mod z to the power n into mod z to the power n. Now, since mod z is greater than r, so mod z would be greater than r, that says is 1 upon mod z would be less than r, 1 upon r. What it says is that this would be less than mod of a n minus 1 upon mod r upon r and so on. We are getting is that it's this last value should be less than mod of a naught upon r to the power n. R is already a positive number, large number, so 1 upon over r, as r to the n is increasing, the power of 1 upon r to the power n, that would be decreasing. So, this would be bounded by, or this would be actually we could find out that is all these things would be limit, or that is this would be bounded by some constant, let us say k 1 times mod z to the power n. Similarly, assume that q is a polynomial of degree m. So, let us say that q is of the form b m z to the power m plus b m minus 1 z to the power m minus 1 so on, plus b 1 z plus b naught. Again in the similar manner we will take z to the power m common. So, what we could write it as b m plus b m minus 1 upon z and so on, plus b 1 upon z to the power m minus 1 plus b naught upon z to the power m into z to the power m. Now, again take the absolute values. So, absolute value, that is mod of qz. Now, here what we are using? We are using the inequality of the mod, that mod of x plus y is always greater than or equal to mod of x minus mod of y, or absolute value of mod of x minus mod of y. So, first we are taking is Bm and all these terms is the second term. So, it should be mod of Bm minus mod of Bm minus 1 upon z and so on, plus B naught upon z to the power m, absolute value of all these into z to the power, absolute value of z to the power m. It says is that this is greater than or equal to Bm, and here what we would be getting is, that is again I am using now the inequality, that mod of x plus mod of y is less than or equal to mod of x plus mod of y. So, since it is in the negative sign, it would be greater than, and we are getting here all the terms Bm minus 1 upon z mod z, Bm B1 upon mod z to the power m minus 1 and so on, B naught mod z to the power m into z to the power mod z to the power m. Now, since mod z is greater than r, 1 upon mod z would be less than 1 upon r. So, minus 1 upon mod z would be greater than 1 upon minus 1 upon r, and like that we just go on. That says is this value in the first absolute first modulus sign, this should be bounded above by some constant k2. So, what we get, this is greater than or equal to k2 times mod z to the power m. Now, my pz is less than or equal to k1 z to the power n, qz is greater than or equal to k2 mod z to the power m, and my fz is mod pz upon qz, and the difference between this m and in the degrees of q and p is at least 2. So, let us assume that it is equal to 2 actually. Then what we would have is, this is less than or equal to mod k upon z square, because k2 upon k1 we are taking it as, let us say, another constant k. Since mod z is greater than r, this should be less than or equal to k upon r square. So, as in the previous case, here also we had obtained that absolute value of fz is bounded above by k upon r square, and the integrand fz e to the power I t z, that is completely bounded by the absolute value of fz, and which is bounded by k by r square. So, now what we have got? We have got this result that this is bounded by this one, and absolute value of fz e to the power I t z, this is less than or equal to absolute value of fz, which is bounded above by k by r square for mod z greater than r equal to r, you could say. So, using the ML inequality on this integral of fz e to the power I t z on this semicircle, that is on this path, using ML inequality, this, since the integrand is bounded by this value k upon r square, this would be less than or equal to k upon r square into the length of the contour S. The contour S is the semicircle, its perimeter would be pi r. So, we are getting it pi r, that is, it is actually k pi upon r. So, what we have got, that this absolute value of the integral fz e to the power I t z on this semicircle S is bounded by k pi by r. Now, this value is positive. As r is becoming large and large, this value would approach to 0. So, what we are getting is that as r is approaching to infinity, the integral of fz e to the power I t z with respect to z on the contour S, this would be approaching to 0. So, what it says is that now integral minus infinity to plus infinity f x e to the power I t x, this would be same as the contour integral, the integral of f z e to the power I t z on the whole contour, closed contour C, which is equal to the 2 pi I times sum of the residues at the poles which are interior to this C, that is the poles which are in the upper half plane. So, we have got that formula. Now, actually what we are evaluating, we were evaluating the function the integral of the form minus infinity to plus infinity f x cos t x and f x sin t x. So, let us using the Euler's formula write this integral as f x cos t x plus I times f x sin t x. Now, what we are getting is this should be equal to now 2 pi I summation of residues of f z e to the power I t z, where summation is over all the poles on the upper half plane. This is also a complex number. So, comparing the real and imaginary part from here, we would get actually the two formulas. One is integral from minus infinity to plus infinity f x cos t x is the real part of 2 pi I summation of residue of f z e to the power I t z, where the summation is over all the poles in the upper half plane. And when we compare the imaginary parts, we do just get is that integral of f x sin t x dx should be the imaginary part of 2 pi I sum of summation of the residues of f z e to the power I t z, where summation is running over all the poles in the upper half plane. So, we have got these two formulas, you could say, or rather than a method where we are reaching, that is, we could obtain these integrals, improper integrals, using the residues of the function f z e to the power I t z in the upper half plane. Let us apply this formulas or this method to some of the examples. Evaluate the integral minus infinity to plus infinity cos s x upon k square plus x square dx and integral minus infinity to plus infinity sin s x upon k square plus x square dx. You see, here in this example we are going to evaluate two integrals. In both the integrals we find out certain similarities. The similarity is the denominator for both this is same, k square plus x square, while the numerator is being changed only to the extent that the numerator of the first integral is cos s x and the numerator of the second integral is sin s x. So, what we could say is we are going to evaluate the integrals of the form f x cos s x and f x sin s x, where of course f x is same as 1 upon k square plus x square. That says is we could apply the method just now we had learned, and both these integrals we can solve using only one complex function, where we would use e to the power I s x. So, f x is 1 upon k square plus x square. The method which we had learned just now, that required certain conditions for f x to get satisfied. The conditions for the f x were that f x should be a rational function, which we could say is that of the form the ratio of two polynomials. Here it is of course a rational function, the numerator is 1, the constant, the denominator is k square plus x square. Certainly a constant can always be treated as a polynomial of degree 0, and the denominator is x square plus k square. So, this is a polynomial of degree 2. One more condition we required on the numerator and denominator, that the none of the factors should be common. Of course, here we are not having any factors common. Moreover, this denominator x square plus k square does not have or does not have any real zeros. Moreover, the degree of the numerator is 0 because it is a constant, and the degree of the denominator is 2. So, the degree condition is also satisfying. That says is that all the conditions of the method just now we have discussed, they are satisfying. So, we could, and moreover here we are finding out that f of minus x is same as f of x also. This condition actually, when we are evaluating this integral from minus infinity to plus infinity, is not really very much required. But if we have to evaluate the improper integral of the form 0 to infinity, then this condition or this even condition of that function is even would be helpful when we are evaluating the integral from 0 to infinity. Then we could say is that the integral 0 to infinity would be half of integral minus infinity to plus infinity of f x cos s x dx. So, let us say apply our method that says is the function we would require as e to the power I s z upon k square plus z square, and we would require to see the poles of this function in the upper half plane and then calculate the residues and use the result with just now the things which we had obtained, that integral minus infinity to plus infinity f x e to the power I t x dx would be 2 pi I times summation of the residues of this function, where the summation would be on all the poles in the upper half plane. So, just using this Cauchy principal value, we would get this result, that is integral minus infinity to plus infinity e to the power I s x upon k square plus x square dx should be 2 pi I times summation of residues of f z e to the power I s z, where the summation would run over all poles in the upper half plane. So, let us see the residues. So, now we have to find out the residue of the function e to the power I s z upon k square plus z square. This function now we will treat as p z upon q z, and here q z is the zeros of this q z implies that is z is equal to plus minus k I when k is, now I am making one assumption because here it was k square. So, whether k is positive or negative, it was not making an effect. Now, let us assume that k is positive. Of course, why I am assuming k is positive, that also you would have got it. If k is positive, then plus k I would be in the upper half plane and minus k I would be in the lower half plane. If k is negative, then actually minus k I would be in the upper half plane. So, without loss of generality, if k is negative, I can say is k is some minus n where n is positive, and thus we can always assume that k to be positive. So, that is we had assumed that let us say k is positive. So, this 0 we would have at plus and minus k. That says is that the function e to the power I s z upon k square plus z square, this will have pole at only one point k I, that is on the imaginary axis at k in the upper half plane. So, we have to calculate the residue at that point. Calculating the residue at that point says is since the function is of the form p z upon q z, we would use the formula of the residue at z naught of any function f z as p z naught upon q dash z naught. What is q dash z here? Q dash z here is 2 z only. So, we would get the residue at k I of f z e to the power I s z as e to the power, that is p k I and upon q dash at k I, that is e to the power I s z is I k upon 2 z, z is I k, that is at z is equal to k I r I k. What it says is in the numerator we would be getting is e to the power minus s k upon 2 I k. This is the residue. So, now let us apply our Cauchy principal value. We got it, that is integral minus infinity to plus infinity e to the power I s x upon k square plus x square dx. This would be 2 pi I residue times residue at k I of f z e to the power I s z. The residue of this one is just now here which we had calculated, this is e to the power minus s k upon 2 I k. So, we just multiply it, that is 2 pi I into e to the power minus s k upon 2 I k. So, 2 I and 2 I got cancel it out, we would get it as pi by k e to the power minus s k. So, what we have got? We have got integral of minus infinity to plus infinity e to the power isx k square plus x square dx is equal to pi upon k e to the power minus sk. What it says is that now this e to the power isk we could write as cos sx plus I sin sx. So, we would get the two integrals, one is cos sx upon k square plus x square dx, another would be the integral minus infinity plus infinity sin sx upon k square plus x dx, and with plus I, that is we would be getting the real and imaginary part. So, compare this real and imaginary part of this. So, this is here we are having two parts, one is real part and another is imaginary part. Real part would be integral from minus infinity to plus infinity cos sx upon k square plus x square, and imaginary part would be sin sx upon k square plus x square, its integral on the range minus infinity to plus infinity. The evaluation we have got only the real number. So, it has only real part, its imaginary part is 0. So, what we had got finally when we are comparing this, that integral minus infinity to plus infinity cos sx upon k square plus x square dx should be pi upon k e to the power minus sk, and the integral of sin sx upon k square plus x square with respect to x on the range minus infinity to plus infinity should be 0. So, we had evaluated it using this residue theory. We had shown that this would be the integral. Now, let us do one more example. And this formulas would be valid when s is positive and k is positive. So, let us do one more example of this kind. Show that integral 0 to infinity of cos x upon x square plus 1 whole square dx is pi upon e. So, now we have to prove this formula. Now, we see that the integral is now from 0 to infinity. The integrand is having one term cos sx and another term is 1 upon x square plus 1 whole square. So, we see that we could write this as the form of fx cos sx kind of integral. So, we have to check about the conditions for fx. If it is satisfying all those conditions, we can move to the method just now we had learned. So, let us see what is my fx. My fx is 1 upon x square plus 1 whole square. Of course, we can say this is a rational function of the form px upon qx, where px is the constant. So, it is a polynomial of degree 0. The denominator qx is x square plus 1 whole square. Certainly, it is also a polynomial whose degree is 4. So, we are having is that the ratio of this is fx is the ratio of two polynomials. None of the polynomials have any factors in common, and the degree of the denominator is 4, degree of the numerator is 0. So, the condition is also satisfied. One more important condition we require, that the denominator should not have 0 on the real line. That is, it should have no real zeros, that roots should not be real. Certainly, x square plus 1 has the roots as plus or minus I. So, we would have the double roots plus I and minus I. So, this is not having any real roots. So, all the conditions are being satisfied. Moreover, since I have to evaluate this integral from 0 to infinity. Now, residue theorem we are applying in the integral from minus infinity to plus infinity. So, for that we have to check one more condition of the even function. If x we are replacing with minus x, this x square will remain as same as x square. So, we are getting is f of x is same as f of minus x for this function, or if I treat this complete integrand cos x upon x square plus 1 whole square. So, if I change x to the minus x, I would get, because cos of minus x is same as cos of x, and this is x square plus 1 whole square, that is this whole function is an even function. That says is, now we could use the condition that integral 0 to infinity of f x dx, where f x is the even function, would be half of 0 to infinity integral f x dx. So, we would be going to use that formula. Now, we want to change this integral to the contour integral. So, we would change this integral to the contour integral of the function e to the power I z upon z square plus 1 square 1 whole square dz, where the contour C is a semicircle bounded by the real line, and that semicircle we would have of the radius r, and that r should be such a large number such that all the poles of this function should be interior to that semicircle. Now, let us see this integrand e to the power I z upon z square plus 1 whole square. The denominator thus has zeros at plus minus I, and both the zeros are of the order 2. So, this function will have only second order poles at z is equal to plus and minus I. So, we can apply the Cauchy principal value, because I would have only one pole of the order 2 in the upper half plane. We could use this integral minus infinity to plus infinity f x e to the power I x dx should be 2 pi I summation of residues of f z e to the power I z. Now, the work remains is to find out the residue of this function at all the poles in the upper half plane. So, let us come to that part. We have to find out the residue of this function e to the power I z upon z square plus 1 whole square. Just now we had seen that this function has only 2 poles of the second order, one is at plus I, another is at minus I. So, on the upper half plane we would have only one pole, this is of order 2. So, whenever we have to find out the residue of a pole of order m greater than 1, we would use this formula. So, we are going to use the formula of finding out the residue at z is equal to z naught of a function f z is nothing but 1 upon factorial m minus 1, the m minus 1 is derivative with respect to z of z minus z naught to the power m into f z evaluated at z is equal to z naught. Here my m is 2. So, m minus 1 would be 1. So, we will use this formula, and now we will calculate the residue at z is equal to I. This is a second order pole. So, I would have m is equal to 2. That says is I would get residue at z is equal to I of the function e to the power I z upon z square plus 1 whole square. Since m is 2, so I would get 1 upon factorial 1, that is 1, and m minus 1 is 1. So, I would get the first derivative, that is d by dz of z minus I whole square into the function e to the power I z upon z square plus 1 whole square. Now, this should be evaluated at z is equal to I. This z square plus 1 we could write as z plus I into z minus I. So, I would get in the numerator in the denominator here z minus I whole square into z plus I whole square. So, z minus I whole square and z minus I whole square would cancel it out. What we would left is d by, that is derivative of with respect to z of the function e I z upon z plus I whole square. It should be evaluated at z is equal to I. So, find out its derivative, not very difficult function. First, the derivative of the first function, it is I e to the power I z upon z plus 1 z plus I whole square. plus the first function into the derivative of the second function. So, e power I z is as such, the derivative of 1 upon z plus I whole square is minus 2 upon z plus I whole cube. This we have to evaluate at z is equal to I. Say if I keep z is equal to I here, I would get e to the power I into I, that is e to the power I square. So, it is e to the power minus 1, and here I would give me I plus I, that is 2 I. So, what we have got I e to the power minus 1 minus 2 e to the power minus 1 upon 2 I whole square, that is 4 I square, and here 2 I whole cube. I square is minus 1. So, we would get it minus I e to the power minus 1 upon 4, and here 1 2 is going to get it, cancel it out, I cube is minus I. So, we would get plus 2 e to plus e to the power minus 1 upon 4 I, that again would give a minus I upon I times e to the power minus 1 upon 4. So, what we have got actually the residue at of the function e to the power I z upon z square plus 1 whole square at z is equal to I as minus I e to the power minus 1 upon 2. Now, use this in our formulation. So, we have got the integral we would get from minus infinity to plus infinity e to the power I x upon x square plus 1 whole square dx as 2 pi I summation of residues of f z e to the power I z, where the summation should run over all the poles in the upper half plane. In the upper half plane, in this particular example, we were having only single pole at I. So, we would just have here the summation will replace only the single value, that is residue at z is equal to I of e to the power I z upon z square plus 1 whole square, and that we had just now calculated as minus I e to the power minus 1 upon 2. So, my integral minus infinity to plus infinity e to the power I x upon x square plus 1 whole square dx has come up as 2 pi I into minus I upon 2 e. I into I is I square, that is minus 1, and 2 is getting cancelled out, we are getting pi upon e. So, again the evaluation of this integral, we have got that value is only the real number, and this integral is actually consisting of two integrals, which is one integral we could say as the real part of this whole integral, and another integral we could say as the imaginary part of this integral. The real part of this integral is cos x upon x square plus 1 whole square dx, integral from minus infinity to plus infinity, and the imaginary part of this integral is integral from minus infinity to plus infinity sin x upon x square plus 1 whole square integrated with respect to x. So, compare both the parts, we would get the real part is equal to the real part, gives me integral minus infinity to plus infinity cos x upon x square plus 1 whole square into dx is equal to pi upon e. So, we were able to prove this formula. So, we have proved the formula minus infinity to plus infinity integral cos x upon x square plus 1 whole square dx is equal to pi upon e. Actually, you can generalize this formula also. You can use here cos ax and here x square plus b whole square, where b is any number. Then you have to find it out that your b, whatever you are choosing, because your pole would be at plus minus bi. So, again b you have to take positive without loss of generality, because if b is negative, you have to use this positive or negative parts in the different manners, that is all. And so, you would be getting here in the formula that whatever you would be achieving the right hand side, the difference of positive or negative only. So, you can generalize this formula using here as cos ax and here as x square plus b whole square, and then do it by yourself. It would be a nice exercise where you could find it out that what the new formula you are achieving, and for that of course a also you would require to be positive. Why? we have done is that is whenever we are taking this function e to the power I s z, we have taken s to be positive and real. So, we do take a positive and b we would take positive, so that we are getting is that our pole b I is coming in the upper half plane. So, for that b we would take as the positive. So, wherever it is coming we take the b positive, so that it would be coming in the upper half plane. So, today we had learned that if our improper integrals are of the form where the integrand we could write as f(x) into cos s(x) or f(x) into sin s(x), and if our integral is from minus infinity to plus infinity, that is it is again an improper integral, then we can use this residue theory again. Of course, we required the method which we had learned today, that f(x) should satisfy certain conditions. Those conditions are that my f(x) should be a rational function, or more precisely my f(x) should be the ratio of two polynomials p(x) and q(x), where p(x) and q(x) should not have any factors common, that is it is in the most reduced form, and the zeros of q(x) should not be real. So that we do have poles only, so that we do not have any isolated singularity for the corresponding complex function e to the power I s z f z on the real line. And then we could use this residue theory and we could find out the integrals. Again, one more condition which was required for us to show that the integral along the semicircle is going to the 0 was that we required the difference between the degrees of the numerator and denominator must be at least 2, that is the degree of the denominator must be higher than the degree of the numerator, and that difference has to be at least 2. So, we had learned one more method to evaluate the improper integral of the form integral minus infinity to plus infinity cos s(x) sin dx, or integral minus infinity to plus infinity sin s(x) dx. We do know that these kind of integrals are occurring when we are finding out the Fourier integrals of the Fourier series. You do remember that many times we do require to evaluate those integrals from 0 to infinity, but if you do remember the Fourier series, if you have done that, the integrals 0 to infinity were occurring when the function was f is either even or odd kind of things, that is we do have f function. If the function f is even, that is we do have f of minus x is equal to f of x, only then we would be having the integral 0 to infinity f(x) cos s(x) dx we can evaluate. When we are not having this even, or we are not satisfying the conditions on the degree or anything, any other conditions which we had imposed on f(x), they are failing, then this method would not apply. Next, we would learn when this condition of degree is failing, a special kind of functions, are the functions we are having is rational functions, but they are of the form this px upon qx, but your condition on the degree, that is the difference between the degree of the numerator and denominator remains at least 2, that is not being satisfied. If it is fails, one special kind of integrals we could solve, that we would see in the next class. So, for today it is all for this one more method of evaluation of improper integrals. Thank you.